When you get a software update on your phone or your computer, are you the sort of person that will instantly update it? Or do you press remind me tomorrow until it gets to a point where your computer says, no more, and shuts itself down at a really annoying time?
I am definitely in the camp of instantly updating. I'm excited to see what's new, what's updated. What about you?
I thought you'd be a defer it. That really surprises me. It will not surprise you that I also do the same because I also get excited about software updates. I think we can assume that software updates are pretty important. But I'm sure you've had it before, like I have, when you update something and you maybe get a new feature, but it makes other things worse.
We've all been there, right? Remember famously a few years ago, a very well-known company sent out an update and then we all had that blue screen of death. But yeah, things happen, right? You try to make things better. There's updates and sometimes it goes completely horribly wrong.
Most of the time you can just go back to the vendor and they'll sort out the problem. But what if the update is fake? What if it's malicious? So this week, Aubrey, we're going to be exploring how security is physically built into our devices to try and stop this happening. I'm Michael Bird.
I'm Aubrey Lovell.
And welcome to Technology Now from HPE. Last week, we explored the importance of post-quantum cryptography, or PQC, as the cool kids say. I think we're cool kids, Aubrey.
I think so. Let's hope. Maybe we're the only ones who think that.
We looked at post-quantum cryptography for governments looking to protect themselves and their citizens. But, like almost every topic we discussed in the show, there is always more to learn. So let's look at this from another perspective.
All right. So in our PQC episodes this year, so far, we've covered the new types of encryption needed to kind of protect against that quantum threat. And then last week, we took a step back to look at the national importance of keeping everything secure against a quantum computer. So have to ask the question, what's next?
This week, we are once again looking at security based around public and private keys, but this time we're considering how the private keys are kept secure, because while they're private for now, if someone were to find a way to calculate them, then the technology they protect could be compromised. And it sort of relates to the question I asked you at the top of the show. So we're going to be catching up with Nigel Edwards, director of the security lab at HPE Labs, later in the show to find out more about this.
And I'm actually looking forward to this. But before we get to Nigel, we're taking it way back. I mean, way back, all the way to ancient Mesopotamia, because it's time for Technology Then. Well, we all know about secret recipes, right? The concept isn't anything new because an ancient Mesopotamian tablet from 3,500 years ago.
Wow.
And written in a language called cuneiform, had a hidden recipe on it for a pottery glaze.
Ooh.
This tablet is the first known use of cryptography to hide secret information, and it used a very simple substitution cipher. So that's where one letter is kind of swapped out for another. Imagine writing a book, but instead of the letter A, you would use the letter L, and instead of B, you would use M, and so on, which is, yeah, that's a lot of work. But, you know, they probably didn't have a lot to do back then.
Aubrey, why is a pottery glaze recipe, why does it need to be kept secret?
I don't know. Maybe it was a really good glaze. Maybe there was the competitor shops and like, my glaze is better than your glaze. And, you know, it's like your grandma's famous mashed potatoes, right? Like nobody's allowed to have them. And it's like guarded for generations, you know, in your kitchen. Anyways, the first properly named cipher we know of is almost a millennium younger than what I'm going to call the Mesopotamian pottery cipher. And this is the Atbash cipher, an ancient Hebrew cipher dating back 2,500 years. We're really working through all the different centuries here. But like the pottery cipher, this was a simple substitution cipher, but it used a mirrored alphabet where the first letter was replaced with the last and the second with the penultimate and so on. This style of encryption would be recreated yet again in what was known as the Caesar cipher, where letters are replaced by another letter and a fixed number of positions down the alphabet. I feel like this is turning into some like crazy movie right now, Michael, where we're like deciphering letters and it's an investigation. But the problem with all of these forms of encryption is that they are easy to break, right? So in fact, you can actually break them by hand using something called a frequency analysis, where you simply look at how many times any letter appears. So in English, the most common letter is E. And once you work out which letter corresponds to E, you can very quickly decrypt something like the Caesar cipher, right?
Oh, yeah. I remember having little puzzle books when I was younger, and they would have little games like this.
Absolutely. As you know, right? Like algorithms today really obviously are far more complex.
Oh, yeah.
Primarily because they need to be, right? Modern computers could use AI to kind of tear that infamous Enigma code to shreds in barely any time. And we've talked about that before on our podcast. So ancient substitution ciphers wouldn't really stand a chance. And the question is, how do we get around the issue of future technology being able to break today's methods of encryption?
That is an excellent question. And really, it's the question for today's episode, because future-proofing anything needing encryption is vital to modern security. So, to that end, I spoke to Nigel Edwards. Nigel is the current director of the security lab at HPE Labs. And we started the conversation by looking at how security is built into our IT estates.
I think what many people are unaware of is that if you take any of our devices, but if we say focus on a server, before a server can even boot the operating system and actually do useful work for the customer, there are a dozen or more firmware modules that need to be loaded into the various components that are in that server. So firmware needs to be loaded into the processor, firmware needs to be loaded into the storage controllers, the network controllers, and the management controller, in our case, the ILO management controller, to bring that server into operation before it can even boot the operating system.
So what exactly is firmware?
So firmware is low-level software that provides management services and operates the components within, let's say, the server. So, for example, a storage controller actually is running software, which we call firmware, that enables it to communicate with the storage devices, get data from the storage devices, and pass that back over an internal bus, the PCI bus in the server, so that the processor can load it into system memory and then start to process on the data.
So the firmware is quite an important component, particularly from a security perspective.
So this firmware is fundamental to the security of the platform. If an attacker could inject their own firmware into the system, potentially it gives them complete control over that platform. And they would be at a level below the operating system, below the level at which any system administrator interacts with the system, below any endpoint protection system. That would allow them potentially to spy on the customer and steal their data and perform other nefarious activities.
Right, so what do we have in place to make sure you can't just load random firmware?
So today, firmware is signed by a private key corresponding to a public key, which is fused or burnt into the silicon. So that means that the storage controller, or ILO, the management controller, for example, is able to verify the signature on the firmware before it installs or loads that firmware. So we know it's coming from the legitimate provider of the firmware. For example, in the case of HPE ILO, the firmware is coming from HPE and it's been signed by HPE.
And so are those keys sort of quite similar to public and private keys when you're talking about HTTPS or encrypting documents?
They're exactly the same algorithms, they're the same kind of keys. So typically we use the well-known RSA algorithm to sign firmware. So it's exactly the same algorithms that are used to secure the web, just a different application.
And when you say burnt in, are we just sort of burnt in through software, or is it physically a piece of hardware that's soldered onto the chip, so to speak?
Yeah, it's a great question. So by burnt in, it means the key is in a piece of immutable memory. Right. It can only be written once, but it can be read many times. So during the manufacture of the chip, this memory is written. Yeah. And it's written with the key that's used which is the public key that corresponds to the private key that's used to sign the legitimate firmware from the legitimate provider of that firmware.
All right, so that key's put on. That sounds like that's perfect. No issues with that. But we have this thing called quantum cryptography,
right?
And that causes issues, right?
So if we take RSA, for example, the security of RSA is dependent on a mathematical problem which is known to be computationally infeasible to run on a classical computer. So in particular, the RSA public key is a long number which consists of the product of two prime numbers. And if you've got the RSA public key on a classical computer, recovering those two prime numbers would take you millions or even trillions of years. But if you could recover those two prime numbers, you can calculate the private key. So you have the signing key. Now, unfortunately for us, there are algorithms which are known to be efficient to run on quantum computers, which are very different models of computation from a classical computer. So in a classical computer, a bit can have precisely two values, 1 or 0. A quantum bit can have potentially an infinite number of values and represent an infinite number of states. And that means it has a very different set of properties allowing us to run different algorithms. So there's an algorithm developed by the American mathematician Peter Shor, which efficiently will recover the prime factors for large numbers on a quantum computer. So instead of millions or trillions of years, potentially hours, if a sufficiently powerful quantum computer is developed to recover the private key from the public RSA key.
Okay, and so when we've talked about this in the past on the show, particularly with regards to software, the answer is, okay, you just rewrite the algorithm. So, when we were talking about encrypting and decrypting files, you just use a quantum compatible method of encryption. But I suppose the problem here is if the method of encryption or the key is burnt into the device, then you can't change that key very easily.
That's right. Once the key is burnt into the device, it's there for the life of the device. So that means the servers that we're shipping today, we cannot change the keys that are fused into the silicon for the operational life of that server.
Okay, so if a quantum computer suddenly appeared, then there are some serious vulnerabilities. And it's not just one vendor, it's every vendor. Everyone creating hardware right now has the same problem, right?
So all the components in a server or a switch or a storage array that load firmware need to be migrated to using additional quantum resistant algorithms in addition to the classical algorithms that they use.
Are they doing that at the moment, or is it all just traditional?
So right now, HPE, as far as I know, is the first company in the industry to announce that they have our ILO management controller, which is using a post-quantum algorithm to verify the firmware that it loads. But generally, no, the devices that are in our servers, our network controllers, for example, our storage controllers, these today are not using quantum-resistant algorithms to verify the firmware that they're loading. So we need to work with our industry partners, our suppliers. It's not something any company can do on its own. Really, it's a call to arms within the industry. We need to migrate all components in all devices, switches, servers, and storage arrays to using these new quantum-resistant algorithms to verify any firmware that they load into these devices.
So how do you know that a quantum resistant algorithm how can you trust that that's going to work when a quantum computer suddenly turns up?
So the quantum resistant algorithms have been standardized by the American National Institute of Standards and Technology, but they're new. Okay, so we believe the maths is sound, but there is a body of opinion within the community and also particularly from the European state security agencies that are advising that because these algorithms haven't been battlefield tested, we cannot discount the possibility that some cryptographer may discover a flaw in them, or perhaps more likely, a flaw is discovered in the implementation. And so what that means is that because we need to be prudent when it comes to security, that at least for the short and medium-term future, we need to run two sets of algorithms. A classical algorithm, such as RSA to sign the firmware, in addition to one of the newer algorithms, such as MLDSA, to sign the firmware. And then the device that's verifying the signatures has to verify both the signatures, and both signatures have to validate before that device will load or install the firmware.
So it's a bit like double locking your front door.
I would say that's a great analogy. Yes, you have to basically two checks that have to take place before firmware is authorized to load into the system.
I mean, even if a quantum computer never turns up, surely that feels like actually quite a sensible thing to do. You're just sort of bolstering the security.
Yeah, I agree with you. I think it's a good thing to do. RSA has been around for many years. People have been analyzing it for many years. But the power of classical computers is improving all the time. And people are still developing new algorithms and new devices in the classical world, which may eventually lead to RSA being weaker than we currently believe it to be.
So how soon do you believe people need to transition to quantum-resistant signing for firmware? And is it realistic that this is going to happen eventually?
Okay, so nobody really knows if and when a quantum computer that can break RSA, and this is known as a cryptographically relevant quantum computer, will be built. So the Global Risk Institute has been surveying experts every year for the last 2 years. So their most recent survey came out in December of last year, and 2/3 of the experts that they surveyed said that by 2039, it was 50% or higher probability that a cryptographically relevant quantum computer would be available. We can't discount that there might be a major breakthrough and that it could occur sooner. So this is why state agencies around the world are now saying to everybody that you need to complete your migration to deploying post-quantum algorithms by 2035 at the latest. And if you're running sensitive systems, then you really need to get it done by the end of 2030. So we need to make sure that all the components in our servers, in our switches, and our storage arrays are using quantum-resistant algorithms as well as classical algorithms like RSA, because over time, it's likely, towards the end of their life, even products that are built in the next few years, will have to coexist and operate in the presence of a quantum computer.
Yeah. So do you think it could already be too late? Do you think there could be a cryptographically relevant quantum computer just
in existence now?
In existence, we just don't know about it.
So our nation state adversaries will certainly not announce to us that they are in possession of a cryptographically relevant quantum computer. So as far as we know, one doesn't exist. Certainly, it's not thought that one exists in the Western world.
Absolutely fascinating. I think I say that every single week. Maybe it's a good sign, but I really enjoyed that conversation with Nigel because I think firmware is not like the most interesting of topics potentially, but it sort of has this sort of hidden implication.
Definitely. What would you say is like your top takeaways from that conversation? I mean, there was just so much information, really good perspective as well on what could happen or what should happen. So I'm curious to hear your thoughts.
The thing that I found most interesting, which is pretty obvious, but actually when you think about it, actually if an attacker can attack the firmware of a device, they would be at the level below the operating system. An attacker could take hold of your, switch or server or whatever it is that is running that piece of firmware, and you as the user could potentially have no idea that they have access to it because the operating system would sit on top of that and be completely unaware. So in terms of an attack vector, if you can get into the firmware, if you can, inject malicious firmware, that is incredibly powerful. I think the second thing is the fact that actually the advice is if you're running particularly sensitive environments, you need to migrate all of the devices that you're using to have quantum resistant algorithms in your firmware. So there are devices running now that could, in theory, be running in the presence of a cryptographically relevant quantum computer, which is worrying. Because I don't know you, I didn't realize that there were pieces of machines that were sort of physically unchangeable. I just thought everything could be updated with a software update, update the firmware, update the software, but this is burnt in.
We have so many devices, Internet of Things. Things are all interconnected and we swap them out. And it seems like it's just more susceptible nowadays to have something like that happen, go undetected, and then really do that viral damage in the background that you're not even aware of. It's almost like a game of chess, right? Like you have to think about what's your offensive, what's your defensive, and always try to be 2 steps ahead of whatever possible outcomes there is.
So I guess the big takeaway here is something that our organizations need to be thinking about We may not necessarily be able to do anything right now because the devices, the hardware isn't there, but we are getting there.
I think it's nice to feel that assurance as well. You know, like it may never happen, but knowing that companies are taking it seriously and putting safeguards in place and thinking about it, I think is super important. It's always in our best interest in technology to be proactive. So it sounds like a lot of those steps are being taken in the right ways.
Yeah, totally. So Aubrey, as you know, I often like to ask our guests when they were younger, what they wanted to be when they grew up. But Aubrey, before we get to Nigel, can I ask you, what did you want to be when you grew up?
You know this answer. I'm going to put you on the spot. This is way back we talk about this.
Oh my goodness. Can you give me a clue?
Okay, what do I talk about all the time that I'm like obsessed with? And especially living in Florida, we have them a lot.
Oh, it's something to do with storms, something to do with hurricanes.
Meteorologist.
Really?
I did. Yeah. I've seriously considered it coming out of high school. What about you?
It's all really transport related. I wanted to be a train driver when I was very young.
Nice.
As everyone does. But when I was older, I seriously considered becoming a pilot. Well, in case you're interested, producer Harry and executive producer Izzy wanted to be a weatherman and a marine biologist, even though Izzy lived nowhere near the sea. Love that. But what I thought was nice about Nigel's answer is that his childhood dream job naturally turned into what he does now. Anyway, take a listen to this.
I found physics and engineering really interesting. So as a 14-year-old, the physics that I was studying wasn't very interesting. And then when I got to about 18 or 19, that was just fascinating. So the kind of whole physics and the mathematics world and all those principles that were becoming, it suddenly got really interesting to me. So I then had great difficulty in choosing between physics and engineering. I chose engineering. But yeah, the 14-year-old Nigel wanted to become a pilot. The 18 and 19-year-old Nigel found mathematics and physics and engineering much more interesting.
Okay, well, that brings us to the end of Technology Now for this week. Thank you so much to our guest, Nigel Edwards. And of course, to our listeners, thank you so much for joining us.
If you've enjoyed this episode, please do let us know. Rate and review wherever you listen to episodes. And if you want to get in contact with us, send an email to technologynow@hp.com. Subject line, Mesopotamian tablets. And don't forget to subscribe so you can listen first every week. Technology Now is hosted by Aubrey Lovell in sunny St. Petersburg, Florida. I'm assuming it's sunny. It's always sunny. And myself, Michael Bird, just outside of London, where the weather is also sunny and really, really hot and humid. Not very nice. This episode was produced by Harry Lampert and Izzy Clark, with production support from Alicia Kempson-Taylor, Becky Bird, Alison Gato, Alyssa Mitchery, and Renee Edwards.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, and Jacqueline Green, and our social media designers are Alejandra Garcia and Ambar Maldonado.
Technology Now is a fresh air production for Hewlett Packard Enterprise. We'll see you at the same time, the same place next week.
Cheers.